And that is a big family picnic. Oh, I used to love those when I used to live near home. We used to have all the little rugrats over and relatives and people you didn't like and did like, but you were related to them. And everybody, and we'd cook hamburgers and hot dogs and barbecue chickens on the grill and all that. And my daddy would always get this big old apron that said best barbecuer on earth on it, a big old cotton apron, and he'd flip the burgers and the hot dogs, and then always he would have one where he was flipping the hamburger and all of a sudden it's going off and he like, use the apron to bounce it back in there, and he'd get himself a big old greasy stain there. And you know when you have kids of every age, they're going to grab the mustard and the ketchup and start squirting each other. And so they squirted the mustard and the ketchup on top of where he had the greasy thing, the greasy stain from flipping the hamburger. Can you ever get that out? Never. If you stain on top of grease, you cannot get it out. And so if you have a bacteria that has a fat layer, even if it's got only 2 layers of cell wall, and you put that crystal violet and it leaks through the fatty layer and gets behind the 2 layers, can you ever get the crystal violet out?
No.
So what do the ones that have a fat layer stain?
Positive.
Gram-positive. Not because they have a thick cell wall, they only have 2 layers, but they have a fat layer on the outside that traps the crystal violet so it can never be removed. Just try it today. Go home, get a nice cotton shirt, smear some butter on it, pour some stain on it, and then spend the next 2 weeks trying to get it out. Because you will never get it all out. So, anyway, that's differential and simple stain. Simple stain just tells, yeah.
Sorry, is bacteria without a cell wall also considered gram variable, or is that just...
No gram stain.
No.
They won't show up anything. They'll be colorless.
So just the level with the knife is that's called gram variable.
Gram variable. It's actually called gram variable on the positive side because 80% of them will take the purple. A few of them will reject both the purple and the yellow because, most of our stains are dissolved in water, so they reject a lot of it. But this crystal violet is dissolved in alcohol. All right, so anyway, we're going to get our smear, our properly prepared smear, and we're going to you're going to go up here and you're going to get methylene blue, and you're going to, by the way, always pick these up by the glass. These droppers, people love to play games and leave them halfway undone, so you get them about here and they go all over you and all over the table. And then the other thing is that the stains themselves, most of them are dissolved in some sort of alcohol and they eat the rubber. So they will fall apart. You have to change the tops about once a year because they all dissolve the rubber. So anyway, you pick up, you have your knife in your gloves, in your outfit. And by the way, where do you do your staining? Most people think we do it on these screen sinks. We do not. We don't because people splatter and because the material that was on those sinks will stick to your slide. So you press this 3 times and you make yourself a little staining area. You lay your slide there and then you take a drop of methylene blue and you put enough to cover the circle. And you let it set there about 60 seconds. Now, 55 seconds is fine, 65 seconds is fine, 120 seconds is fine. It's not that exact, but not 10. So, you're going to leave it on about 60 seconds, and then when you're done, you're going to pick up the slide and you're going to shake it off into the sink. Shake it off. And then you're going to take the water bottle that we have, and if this is your slide, and here's your little circle, you're going to aim the water here and here and let it run down. You are not going to aim it at the circle. That will overwash it. And we do have a terrible problem with about 90% of you. 90% of you are freaks. It's got to be clean! Clean, I say! Every bit of it. Gone, gone, gone. It's not good for staining. You can wash it all off. So what we want you to do is aim it above and let it run down until the water is pastel, still barely blue. Stop, shake the rest of the water off, take a piece of paper towel, fold it over and blot it dry. Don't scrub, just blot. Then put the oil on it and focus it. And you focus it by putting it in the slide holder, bringing the condenser up. You've already got the oil on. And click the 10X into place, bring the stage all the way up, and then all you have to do is go down just a little bit and fine tune. Swing the oil objective into place, fine tune, there you go. So the simple stain tells you size and shape. Now in virology, we also use the methylene blue simple stain. And we use it because viruses need host cells, and we grow a lot of bacterial viruses. And we want to know if the virus is killing the host cell, because when it kills it, it's released, and we get high virus production. So we often stain a liquid containing our cells with methylene blue, because living cells in their first 5 minutes after receiving methylene blue are baby blue. However, they're killed by methylene blue. So in 15 minutes, they're all dark blue, navy blue, or black. So another sort of FYI is that methylene blue will kill living cells. Living ones will be light blue, dead ones will be dark blue or black. Now, guess what? You didn't think any of this applied to real life? It does. When we didn't have all the fancy antiseptics and antibiotic ointments and Bactrin and all those triple antibiotic ointments for when you cut your finger, you know what we did? We sprayed it with crystal violet or methylene blue. Even today, farmers, if a cow gets tangled up in barbed wire, what do? We get the barbed wire, we cut it away, we put her in a chute to hold her, and then we wash it with Hicks, and we spray it with crystal violet, because crystal violet kills bacteria. Methylene blue does too. These dyes were once used as antiseptics and disinfectants. Disinfectants are on dead things, antiseptic is on living tissue. Why don't we use it anymore? Not many people want to walk around with big purple stains on their body where they scratch themselves. So we don't use it for people now, just for aesthetics. But it is a very, very good way of killing bacteria, the dyes that we use here. Okay, so key thing, don't overwash. How can you tell if you've overwashed? It will look like bleached jeans. And that's where you have either used too strong a stream of water or hit this. Or you sprayed it up here, but you kept washing until the water came off clear. It will not be bright blue with a white background, which is what we want. Questions about the simple stain? Okay, so we're not going to go into, again, like I said, we're not going to go into the gram stain tonight because that's going to be an entire class. But after Tuesday, I would like for you to look at how to do a gram stain and read a little bit about the thickness of the cell wall and the fat-covered one, tuberculosis, mycobacterium, and the 8 steps to do it, because there will be a tremendous amount of test questions on the lab practical about the most important stain in all of microbiology, the gram stain. The second question a doctor asks you, ask the nurse or whatever, the first thing is, do you think it's bacteria? The second thing is, what's the gram stain if it is bacteria? So, gram stain is really, really important. All right, so that is the end of anything about lecture, any lecture about lab tonight or the cards. What cards should you make for the next time? Gram, Indusfor, acid fast, but we won't be going over them because we'll be having a test and we'll be going further on into the chapter on the microscope. So you really basically have a week to do those things. And they're already done and other things. Oh, one of the things I told the other class that I didn't tell you, and that's because I like them better, was that if you are one, if you're very thorough, two, if you're like me, always looking for a shortcut, even though it hurts you, you will have perused the website like I told you to and looked under every button, and you will have found the cards are already there and already done. But it won't do you any damn bit of good. It is for this. Do your own. Put your own there. Put it in your own words. That's what you'll remember. But then you can go to mine and see if you left anything out. But don't start with just mine and make yours from it, because you won't learn anything and it won't stick. Do it the right way. But you can do it any way you want. You'll pay the price. All right, so let's go with what we were doing tonight, and that's the lecture on introductory notes.
I have a question.
Yeah.
So what cards are we supposed to have done already?
Right now, you should have done how to properly wash a slide, preparation of a smear from agar, preparation of a smear from broth, the simple stain and the negative stain. And by a week from today, you should have the gram stain and the spore stain and acid.
And all this going to be on the test?
The only thing what's going to be on the test is from boing, this point backwards.
Okay.
Everything from now backwards except for the discussion about the gram stain.
Mm-hmm.
Okay?
Now, do you want the cards as an actual card already? Are we turning
Not
these
yet.
in? Or?
When we get to next Thursday, I would like for you to have them either on a sheet of paper typed out so you can follow the instructions. After that, you should be taking these and moving them to however way you want to design your lab book. But we will be doing, in class next Thursday, how to focus a microscope, which we will be talking about tonight. 2, the smear from agar, how to wash a slide, the simple stain, and maybe the gram. All right, so we're finishing up introductory notes tonight, and the last thing that we went over was the word natural. Am I right? Anybody have any questions about natural? Remember, natural means of Mother Nature, not processed in any way, directly as it came from the dirt, if it's something that grew there. It does not mean any of the advertising things that we think it does, pure, good, cures, simple, non-toxic, doesn't have chemicals, all the things they try to advertise that only idiots believe. Other things that are often confused with the word natural is the word organic, and the word organic means only contains carbon. In real life, the word organic has become meaning does not contain pesticides, herbicides, poisons, or artificial fertilizer. And as far as I know, there's nothing, unless you do that at home, that is exactly that. We do have California certified organic, which means it has been tested by every chemical means. At least one sample has from that farm, and they have not found traces of any poisons, herbicides, pesticides. They do not test for artificial fertilizer. The farmer is also certified that they don't use pesticides or herbicides or other poisons. And finally, the farm has been inspected by the state of California. So those you find mostly at farmers market, and they will have a sign, California Certified Organic. Then there's USDA Certified Organic and USDA Certified Organic. There's only one thing you can count on. The farmer has signed a statement that they do not do this. They do not use poisons like pesticides and herbicides. They are supposed to be checked at least once every 10 years by using the methodology of the U.S. Department of Agriculture, which is not as good as the best methods known. They're always behind. They measure much larger quantities as being the smallest ones. And they are supposed to be inspected, but if you remember from the salmonella scare with all the eggs, those people that died from that egg farm, I believe it was in Iowa, that thing had been in business 30 years and had never been inspected. So, so USDA certified just means that a farmer pledges that it hasn't been, and hopefully the fruit or produce have been tested by USDA methods, and there may have been a visit to the farm. But there is no policeman in either spot. And then GMO means genetically modified organisms, and are genetically modified foods. And there are 2 points of view in the world about that. In Europe, you can do any experiments you want on it, but you cannot sell it. In the United States, the experiments are highly regulated, but once they're approved, they can be sold and they are not labeled. So 2 widely different points of views, and there are some problems with genetically modified food, particularly the ones with the insecticide in corn, but in most cases, no one can hypothesize or find any proof on how it causes any harm to put a gene that doesn't produce anything like, like the fish gene, for instance. The one that produces an insecticide we are a bit worried about, but the ones that produce a vitamin or produce or prevent it from rotting, no one can come up with any idea how that could be harmful.
I have a question about GMO products. Do they carry the same nutritions that, like regular tomato, for example, like organic, without any genes? And
It depends on the product. In almost all cases, the purpose of a genetically modified food is to either make it more nutritious or give it more taste. So, or more production, but usually production we've already done. We've got tremendously producing foods, they just don't taste good. And a lot of them don't have much nutrition in them anymore, because we selected strains, but they're not modified. All right, so anyway, we're going to move on. The next one is laws. And remember, we were going over the definition of science. Science is the organized systematic study of the natural laws of the universe. And the word universe means everything that exists, whether or not we can detect it. And the word law in science means that something that is true, was true, and always will be true. It's immutable, unchangeable. It is the facts on how the universe functions. So, legal laws can be changed or ignored. Scientific laws, no one can ignore them. No one can change them. They can't be altered. They are there, and they will always be there. The key point is the next one. Remember, organized systematic study of the natural laws of the universe, and universe is everything that it is. And the last third of the essay is this part that says, how do we move from a hypothesis to a scientific law? And this is called the character, nature, or process of science. And there is one super major thing you must know. It is not linear. You don't come up with a hypothesis, do a couple of hundred experiments, find out you're right, everybody agrees, restates it into a more general theory, do a few more experiments, everybody agrees the theory is okay, and it becomes an immutable, unchangeable scientific law. In 2,000 years, we have 7. They're all in physics and in chemistry. Matter can neither be created nor destroyed, only changed from one form to the other. The amount of entropy in the universe is constant. The gas laws, all those things. We've only discovered a few. So there is no straight line from hypothesis to theory to scientific law. It is hugely amount of where you come up with a hypothesis, they do a couple of hundred experiments, everybody thinks you're right, and that is wonderful, and they restate it as a theory, and somebody tests the theory, and the hypothesis does it a better way and find out they were completely wrong and they have to start all over. Science is a series of previously accepted inaccuracies. It is not history. It's in continuous revision. We will probably never be able to, I mean, you know, we're finding out infinitesimal spots, parts of the Empire State Building kind of thing. We're finding out how one brick is made in this gigantic structure of things, and it took 1,000 years. So remember that number one, science is not history. History is unchangeable. You can't go back and change who won certain war. Science is always changing. The more we know, the more we find out. We were slightly wrong, we need to revise. Yeah?
So how would you say laws or natural laws are immutable if a scientific approach or theory is going to be disproved someday?
We always are waiting to be disproven, even though we think we've come up with a law. Like right now, there is a generalized theory. And remember, there's a difference between a theory and a generalized theory. A theory explains one thing. A generalized theory unites almost all of science and explains many different things uniquely, short, and concisely, and has never been disproven or had anything that disproves it. There's only one that I know of right now. Anybody know what it is?
Gravity?
No.
Actually, gravity on Earth or on a planet is accepted as a law. The law of gravity on Earth, you have to say. You can't say the law of gravity on all planets. But what generalized theory is basically within an super, 1 second in time of being a scientific law. It used to be called evolution, natural selection. All of modern science is based on natural selection. If you don't believe in natural selection, stop using antibiotics. Stop using half the medical discoveries that we have, because they're all based on the fact that evolution is true. Yes, every step in evolution has not been discovered, but the general structure of it has been, never been disproven, and you can actually do scientific experiments to prove great, huge leaps of it. And if it wasn't true, then modern science wouldn't exist. So there's so many things that support the theory of natural selection that it is almost a scientific law. But anyway, remember that, I always love this, they say that a scientific humorist. That's an oxymoron, isn't it? I mean, have you ever seen a scientist that was humorous? It's like military intelligence. Doesn't exist, okay? So, a scientific humorist was a person that came up with this idea that science is a set of previously accepted inaccuracies. Think about that. We once really believed this was true, but now we find we were inaccurate and have to revise. So remember, it's in continuous revision. We come up with experiments and hundreds of them, and people copy them and do them, and everybody believes it's right, and then one guy comes up and blows everybody out of the water, and they start all over again. And so it happens all the time. Let me give you, my mother just gets so frustrated by this, because she's the only one my mother, my sister, all my nephews, and niece, none of them have a clue about anything in science. I don't know how they lived with us and didn't come up with anything. But my father and I are like aliens to the rest of them. And my mother is always so angry about science. Of course, she listens to Fox News every day, 24/7. But anyway, she came to me once and said, you know, I am so angry. And I said, why? And she says, well, they've been lying to me all these years. And I said, what? She says, you know. And I said, what? Your sister and my breast cancer. And I said, where's the lie? And she said, well, they found out, you know, women of a certain age have menopause when they begin lowering production of estrogen. And it is horrible for a lot of people. It's really bad. Hot flashes, nervousness, passing out, dry skin, drying of everything. You know what I mean? Just tremendous problems, wild mood swings, anger. Many actually, you know, go into what you might say was manic and then depression kind of things. And my mom had an incredibly difficult time. And scientists discovered that this was the change in your body's production of estrogen. So they thought, well, then what will we do? We'll do just like we do with nicotine or getting you off drugs or alcohol. We'll wean you off of it. We'll give you a little estrogen and gradually, over time, remove it, and you will adjust better, but you won't suffer as much. And so she began taking Primarin, which is an artificial estrogen, and it did help with the menopause, and it was fine, and after 7 years, she went off of it, and then at 80, she developed breast cancer. And the way she found out she had breast cancer was at 50, my sister discovered a lump and went and had a biopsy and found that not only did she have breast cancer, but she had the breast cancer gene and the one that was fed by estrogen, and she had been using the estrogen birth control patch for many years. And so my sister decided to go ahead and have a double mastectomy with reconstruction, and it was successful, but she still takes the pill that removes estrogen from her body just in case there's a few cells that still are fed by the estrogen. And after she went through all of this horrendous, and by the way, she had no health insurance because she had been divorced and her health insurance went with the divorce. But she had it through her husband. Yeah, I know. And so, anyway, she was 3 years into her breast cancer when she and my mom were out swimming, and they were in the changing room, and my mother was, you know, lifting her arms like this, and my sister said, "What's that?" And my mother said, "Oh, it's just a little lump kind of thing," and my sister felt it. She said, "Oh my God, that feels exactly like mine." And so they went and did the biopsy, and my mother had the aggressive kind, same gene, estrogen caused. And she had a mastectomy, a single mastectomy, and now they've both been cancer-free for 7 years, but they're still taking the pill that absorbs estrogen. So she said, you know, this is really awful because we had this disease that was caused by a lack of estrogen. They gave us artificial estrogen, but then we got another disease because of it, and now we're taking a pill that removes estrogen. And she said, you know, this is all just corruption and horrible. And I said, no, it isn't. It's the best we knew at the time. It's what we thought. But it's not bad science. It's revised science. And now we know, and we try to test people for this gene to make sure they don't take any estrogen, birth control products, or that sort of thing, if they have the gene. Which, of course, you know, we had recently had a movie star that not only had that gene, but another recessive gene that causes breast cancer. Another one was caffeine. Originally, when we discovered that caffeine was in coffee and other things, the big push in advertising was it gives you more intelligence. It enables you to concentrate better. it's better to have caffeine in your system a little bit in the time, all the time, for your functioning as an individual. And then, in the 50s, they discovered DNA, and they discovered the caffeine molecule is very similar to one of the DNA bases, and without any experimental proof at all, they hypothesized that women who become pregnant should not have caffeine because the incorporation of the fetus of these DNA bases might be confused, and they might incorporate caffeine instead of one of the DNA bases, and it would result in birth defects. So even to this day, sort of like that old wives' tale about you can get the flu from the flu vaccine, pregnant women don't drink coffee or tea because they should avoid caffeine, even though it has been disproved that it's been shown that this is not true. Well, then it was discovered that caffeine also causes irregular and speeded up heartbeat, and it was hypothesized that people that have arrhythmia or have had a bypass should not have caffeine because it puts stress on the heart. And so then, my father, who had just had a quadruple bypass, was taken off of caffeine, and he was despondent. He said he'd rather drink dirty sock water than drink decaf. And he said he could tell the difference, and it was awful and garbage, and his life was ruined and all this. And then they did a study on nurses in Norway, 70,000 nurses over 7 years, and they found that nurses, which drink more coffee than anybody, it caused no harm, no birth defects, no problems even with the ones that had heart problems or arrhythmia. And they came to the conclusion that the same thing your mother told you when you were growing up, don't do anything in excess, everything in moderation. A few cups a day is not going to hurt anybody at any time. Certainly don't exceed 6 cups a day. And they discovered in this study that there is one extremely rare subtype, genetic subtype, that when they drink an excess amount of caffeine can have a spontaneous heart stoppage. But it can't be tested for, and if you follow the general guidelines of moderation, less than 6 cups a day, you shouldn't, even if you have this subtype, have a problem. So this is a whole bunch of experiments over a whole bunch of times that have led to different conclusions, and at this point we're in the idea that caffeine is of real no particular difficulty. Now, of course, do not do what everyone thinks you can do. Go out and get your ass bliss-ass drunk and then start drinking espresso. All you'll be is a wired drunk. Drinking coffee does not sober you up. In fact, it does worse, because you will be a wired drunk, and coffee is a diuretic, so you lose water with coffee, and that's the problem with drinking alcohol, is your brain is dehydrated. So the best thing to do if you get a little loopy is drink a Coke with a little sugar in it and stuff like that, and then start pushing Gatorade or some nice balanced salt-containing fluid for a couple of hours, and you will push it on through and sort of rehydrate things. But don't be drinking a pot of coffee after 16 beers and thinking you can drive. So anyway, the other big thing about where experiments have changed is in the 1940s we discovered that cancer is caused by altered DNA, damaged DNA. And even though cancer is 125 different diseases with the same name, they have one similar characteristic, and that is cells lose the ability to control reproduction. Normally when cells touch each other, they stop reproducing. It's called contact inhibition. Cells that have lost that pile up on top of each other and seed out, and can either no longer function or can be defective and cause tumors in other areas. And one of the things that they discovered is a byproduct of oxidative metabolism. In other words, metabolism in the presence of oxygen produces free radicals. And free radicals damage DNA and can cause the loss of contact inhibition. So, the natural process of generating energy in an oxidative environment produces free radicals that damage DNA, and accumulation of this damage can result in cancer. In the 50s, they discovered antioxidant vitamins destroy free radicals, and that a molecule of an antioxidant can remove as much as 100,000 free radicals. So they began pushing large doses of antioxidant vitamins like vitamin C and beta carotene, thinking that it would reduce cancer rates by getting rid of the naturally formed cancer-causing free radicals. Except after 30 years of having people take excess amounts of vitamin C and beta carotene, there was no change in the cancer rates. And this was astounding. So, a study was done in Scandinavia in which the Norwegians divided 70,000 people into three groups for 10 years. The first group got the regular, which is quite healthy, Norwegian diet with vegetables and very little fat and less red meat and, omega vitamins with the fish oil and all that. And the second group got the regular Norwegian diet, but a larger amount of the dark green vegetables that produce beta carotene. And the third group got the normal Norwegian diet, but they got the same amount of beta carotene by pill form. And followed over 10 years, they discovered one group had lower cancer rates. Only the group that got the beta carotene from their diet, the excess beta carotene from their diet, had lower cancer rates. So the original theory was correct, but taking it in pill form didn't work. An example of how we had to revise our science and someone came up with a better idea. So, remember that science is a whole bunch of backward circles, backward steps, and revisions, and very rarely do we inch forward. And when we inch forward, even when we jump forward by a great leap, we may fall backward. Recently, not that recently, but Big Bang. Does everybody know about this theory? Yeah, there's only one on the creation of the universe. It's called the Big Bang. That's it. Creationism is not a scientific theory about the universe. And Big Bang does not interfere with religion. It just says that in the beginning, all matter and everything that is in the universe was concentrated in an infinitesimally, inconceivably small dot that was spinning around at very high speeds and exploded and flung all matter out. And when this matter was flung out, is when the first light and the first atoms came into being. And so it explains the fact that the universe is expanding. And you can basically hypothesize if we are here, and this is the theoretical center, and light moves at a certain speed, how long would it take us to get here? And you can extrapolate back and come up with an idea of how long it's been since the Big Bang. It doesn't have to conflict with religion, because remember, where did the dot come from? God, whatever you want. All we're talking about is, after the dot was there, what happened? So, if you take where we are now and the speed we travel from this theoretical center, you come up with between 15 and 22 billion years to get where we are. Not a terrifically great number. That's a wide variation. And Another thing you can look at is the AT&T discovered that there's what we call spectral shift. And that is, if something is moving away from you, it shifts white light toward one direction in the spectrum. And if it's moving towards you, it shifts the light to a slightly other direction. And so you can plot how things are moving in the universe, and the universe is expanding. And then if you look at the very edge of the universe, you can see that that it is moving at a constant rate outward. Well, all of this was just wonderful, and it gave us an idea of how long it's been to the Big Bang, but it took a man by the name, he'll come to me in a moment. Anyway, in about, I think it was 1977, there are people that think in unique ways. And sometimes when I hear about it, I just want to go, wow. This guy, I wish I could think of his name, it'll come to me in a minute. He said, instead of trying to do all those things to figure out how long it's been since the Big Bang, or how old the universe is, or anything like that, why don't we do this? Why don't we say, if there was a Big Bang, then there must be this. And so that's what he did. He said, if there was a Big Bang, then where the different galaxies exist today should be hot spots. That's where the matter was flung outward in a spiral pattern. And so if you point a telescope or a recording device that can look as far back as possible. Remember, you're looking through a time machine because light travels at a certain speed. So if you look back as far as we can possibly look and take a picture of what the universe looked like a few seconds after the Big Bang, and then look at where those little slightly hotter areas are, if there today is where the galaxies are, then that will tell us that that is what happened. And so they sent up a satellite, and it's called the relic radiation theory. And it says that if you take a picture of the universe in its infancy, the slightly hotter dot spots will be where the galaxies exist today. So they did, and it is. And they came up with the idea that it was 13.2 billion years old. But last year, the European Space Agency sent up a better satellite, and this satellite took a clearer picture of back, and now it is 12.7 billion years old. So this is where we've gone in this progression. First, measuring the speed of how things are moving apart from each other and extrapolating backward, and then looking at what it looked like, the hot spots of where it looked like, and proposing an even better theory. So right now, they think the universe, the Big Bang, happened 12.7 billion years ago. And of course, a lot of people that are religious, like myself, think that that's really unique because in the first chapter of Genesis, what does it say? In the beginning, there was light. And that's exactly what happened. Right after this Big Bang is when that first light appeared, and the atoms then became into existence. And there was only hydrogen and helium. So it is really, really interesting how this stuff sort of piles up on each other and supports each other. So any question about what is the character, nature, or process of science? How does science get from a hypothesis to a theory to a scientific law? Yes, it passes through those three steps, but is it linear? A straight line? Is it quick? Do we have lots of laws?
No.
It's a continuous revision. Any questions? Okay, so that is what ends all of the Chapter A, Test A material. And what I talked about in the last hour and 15 minutes or so is the microscope chapter. And we're going to start. We're not going to get terribly far in this, but we are going to show you some things about the microscope that we have and so forth. And we're going to talk about, starting at the very beginning here, remember that the study of the microscope is called microscopy. And the man who came up with the first microscope is Anton von Leeuwenhoek. And Anton was an asshole. I've had the privilege of meeting and knowing some Nobel Prize winners and some very famous scientists. And one of the things I have discovered is that, like most of our heroes, they are not perfect. Now, I guess if I was to say who is my biggest hero in my belief system, it would be Franklin Roosevelt. I mean, you know, he had polio, he became president of the United States, hardly anyone knew he had polio. He gave us the land-grant university system, he came up with the idea for the interstate system, he gave us Social Security, he brought us out of the Great Depression, and he kicked ass in World War II. I mean, you know, maybe my second one would be Bill Clinton. Well, guess what? They both had some very serious errors in the same area. You see, when Mr. Roosevelt died, he was in the arms of his girlfriend. And so they had to run and first grab her, throw her in the closet and hide her, then run and grab Eleanor and find her because she had a completely separate life, squeeze some lemon or lime in her eye, make sure she looked a little crybaby, and take a picture. Oh God, Michael is dead! Okay? So, you know, Mr. Clinton had a little hanky-panky problem too. Both of which I think were very great men, but one of the things you need to realize about people that you admire is they may have some incredible attributes that nobody else has, but they're just like the rest of us with their faults. And so Mr. Leeuwenhoek made a great and grand discovery, the microbial world. He was the first one to see things smaller than the eye can see. Now, Mr. Leeuwenhoek was a nasty little guy. He was a rich eyeglass maker in Holland, and he put these lenses together. First, he just used a magnifying glass, and later he did put two of them together, so it became compound. But the original was a single lens scope, and he observed what he called animalcules, little small, he thought, animals. And he observed these things, but he built a single microscope for every one thing he wanted to look at. So when he was looking at pond water, I guess he had to build real quick, because that stuff would evaporate. Remember, he didn't have an interchangeable stage, so he built the microscope around what he wanted to look at. And he was an amazing draftsman. What's the difference between a draftsman and an artist? An artist uses imagination and interprets the beauty they see, and they do not exactly copy it on canvas. They interpret it. A draftsman is like a copy machine. They copy something exactly. He was a draftsman. Whatever he saw, he made incredibly detailed, beautiful drawings of it. People called him a big fat liar. And he got into real trouble, thank God he was a Protestant. Because the church said God would not create anything smaller than its greatest creation man could see. There was nothing smaller than we can see. There were no microbes. He was a heretic because he said There were things smaller than the eye can see. And the church's position was, we are God's greatest creation. We are made in the image of God. And as such, God would not make anything smaller than man's eye could see. Which I think is hilarious, because think of this. Why are we putting limits on God, which we say is omnipotent? But never mind. So anyway, Leeuwenhoek was a real selfish dude. He was very rich. He made these microscopes. He made wonderful drawings, and everybody called him a big fat liar, and he didn't care. I guess he didn't have a small ego. He would not share. He would not let anyone see his microscope or handle them. As a result, during his lifetime, the microscope was not improved. Remember, it takes more people looking at something to improve something. Near his death, his daughter said to him, "Dad, you're not going to be remembered well." I mean, these are great, these are wonderful, but and you publish and people think you're an idiot and making it all up, and you won't share. You know, he didn't take Sandbox 101, where you learn to share. And so, near the end of his life, his daughter convinced him to allow scientists from the British Academy of Science to come to his laboratory and observe through his microscopes. But he was so afraid they would steal them. Remember, they were only about 1 inch by 2. And he was afraid they would adjust the focus because it was just fine for his eyes. That he tied their hands behind their backs before he would let them look through his microscope. So when he died, his daughter sent them to anybody, and they rapidly were improved. And by 1845, the microscope reached its pinnacle of creation. The microscope, the compound light microscope that we have, cannot be improved any more than existed in 1845 when they first added the electric light to it. They used mirrors for a while. But once they added electric light, and that really only intensified the light, it didn't really improve anything about clarity, the microscope reached the maximum of its creation. It is limited by the laws of physics. We can only see certain wavelengths. And those any wavelengths any shorter than what we can see would give us greater detail, but the problem is we can't see it. So if you can't see it, then there is no use in having it, right? If I could show you greater detail than your eye could see, would it matter? No. So the laws of physics limit the compound light microscope. One of the, okay, for micro 1 and micro 40 or what?
Just 40.
Just 40? I think I have a couple of them scrambling around in here somewhere. There's one. There you go.
Sorry, thank you.
No problem at all.
Thank you, I appreciate it.
Anytime, you guys just come in and something comes up, doesn't bother me, follows them. That's all right. All right, so anyway, one of the things that limit the microscope is the wavelengths of light. Remember that white light is all the colors combined, right? And black is the absence of light. And what's the shortest wavelength you can see? What color is it? Purple. Remember, when you get to light, this is the spectrum. Energy moves through the universe in waves. And really, really short waves are damaging to living things, like gamma rays and X-rays and ultraviolet. All those things will damage you. But the shorter waves have a lot of energy in them. And how do we see things? We bounce light off of them. So if the wavelength of light that hits a line, and two lines are drawn very close together, If it can pass between them and bounce back, you can see them as two lines. But if the wave is so wide, the two lines, it can't get between them, you will see it as one fuzzy one. Everybody kind of get that? It's called resolution. So the shorter the wavelength, the more detail you're going to see. And the longer the wavelength, the less detail you're going to see. So we don't want to use long wavelength light up here. This is why when you turn on your light bulb in a microscope, it is purple or bluish purple. Let's just put it in real life. I'm 62 and I'm single again. This is not good. I mean, you know, I am perfectly happy. I'm ecstatic, but it would be nice to share a life with somebody. Certainly not 24/7, my God, I couldn't stand that. But, you know, somewhat. So, on Friday nights, I try to go out to meet people. Now, I do not go to one of those fancy bars on Sunset Boulevard where you have all glass and all that. I go to a bar that's painted black, that has little red lamps on all the tables and has dark wood around it. Why? Because under red light, honey, I look fabulous. No wrinkles, nothing. When Barbara Wawa interviews one of those famous movie stars, what does she have? A nice overstuffed couch, a lamp with a yellow light on them. Do they put her under white, bluish white fluorescence like what's projected here? Hell no. Just think about this. At 1:45 in the morning and you're at the bar and they say last call for alcohol. You do not stay until they flip on the fluorescence. Do you know what you look like under blue-white fluorescence? After you've been drinking all night? Even with beer goggles, people do not look pretty. So, remember, the longer the wavelength, the less detail you're going to see, the less wrinkles, the more young I'm going to appear. Now, if you're in a hospital situation, what do they do in a hospital? They have blue fluorescent lights like the one coming out of this, has short wavelengths, and the walls are painted either light green or light yellow. Why? Light green or light yellow shows true skin color. Bluish or purplish white fluorescents give you the greatest detail so you can see whether people are dehydrated. When you're dehydrated, you're highly wrinkled. That's why examination rooms are painted green or yellow with the sort of bluish purple fluorescent lights. The bluish purple gives you short wavelengths showing you lots of detail, and true skin color comes from a yellow or green light pastel wall. So if you want to see the greatest detail with your microscope, you're going to need a filter or a light bulb that is here. Why? What does that mean? I can have two lines drawn 0.42 microns apart and see them as two lines because the beam will pass between them. If I take that same two lines that are 0.42 microns apart and shine red light on them, I'll see one fuzzy line. It won't go between. All right, so backwards. Standard unit in microbiology. Every study has a standard unit. What's the standard unit of the metric system? The name's in it. Meter. And what's the standard unit of the English measuring system? Foot. All right, so when bacteriology became a science of itself, and by the way, do you know what the real name of this class should be? Bacteriology and a few other small things. Why? Because we don't teach microbiology, we don't have time or the equipment. Microbiology is fungi, protists, bacteria, viruses, prions, viroids, all those, and that is a big family picnic. Oh, I used to love those when I used to live near home. We used to have all the little rugrats over and relatives and people you didn't like and did like, but you were related to them. And everybody, and we'd cook hamburgers and hot dogs and barbecue chickens on the grill and all that. And my daddy would always get this big old apron that said best barbecuer on earth on it, a big old cotton apron, and he'd flip the burgers and the hot dogs, and then always he would have one where he was flipping the hamburger and all of a sudden it's going off and he like, you know, use the apron to bounce it back in there and he'd get himself a big old greasy stain there. And you know when you have kids of every age, they're going to grab the mustard and the ketchup and start squirting each other. And so they squirted the mustard and the ketchup on top of where he had the greasy thing, the greasy stain from flipping the hamburger. Can you ever get that out? Never. If you stain on top of grease, you cannot get it out. And so if you have a bacteria that has a fat layer, even if it's got only 2 layers of cell wall, and you put that crystal violet and it leaks through the fatty layer and gets behind the 2 layers, can you ever get the crystal violet out?
No.
So what do the ones that have a fat layer stain?
Positive.
Gram-positive. Not because they have a thick cell wall, they only have 2 layers, but they have a fat layer on the outside that traps the crystal violet so it can never be removed. Just try it today. Go home, get a nice cotton shirt, smear some butter on it, pour some stain on it, and then spend the next 2 weeks trying to get it out. Because you will never get it all out. So, anyway, that's differential and simple stain. Simple stain just tells you,
Sorry, is bacteria without a cell wall also considered gram variable, or is that just?
no gram stain.
No.
They won't show up anything. They'll be colorless.
So just the one with the negative is that's called gram variable.
Gram variable. It's actually called gram variable on the positive side because 80% of them will take the purple. Today, farmers, if a cow gets tangled up in barbed wire, what do? We get the barbed wire, we cut it away, we put her in a chute to hold her, and then we wash it with Hicks and we spray it with crystal violet because crystal violet kills bacteria. Methylene blue does too. These dyes were once used as antiseptics and disinfectants. Disinfectants are on dead things, antiseptic is on living tissue. Why don't we use it anymore? Not many people want to walk around with big purple stains on their body where they scratch themselves. So we don't use it for people now, just for aesthetics. But it is a very, very good way of killing bacteria, the dyes that we use here. Okay, so key thing, don't overwash. How can you tell if you've overwashed? It will look like bleached jeans. And that's where you have either used too strong a stream of water or hit this. Or you sprayed it up here, but you kept washing until the water came off clear. It will not be bright blue with a white background, which is what we want. Questions about the simple stain? Okay, so we're not going to go into, again, like I said, we're not going to go into the gram stain tonight because that's going to be an entire class. But after Tuesday, I would like for you to look at how to do a gram stain and read a little bit about the thickness of the cell wall and the fat-covered one, tuberculosis, mycobacterium, and the 8 steps to do it, because there will be a tremendous amount of test questions on the lab practical about the most important stain in all of microbiology, the gram stain. The second question a doctor asks you, asks the nurse or whatever, the first thing is, do you think it's bacteria? The second thing is, what's the gram stain if it is bacteria? So, gram stain is really, really important. All right, so that is the end of anything about lecture, any lecture about lab tonight. A few of them will reject both the purple and the yellow because, most of our stains are dissolved in water, so they reject a lot of it, but this crystal violet is dissolved in alcohol. All right, so anyway, we're gonna get our smear, our properly prepared smear, and you're gonna go up here and you're going to get methylene blue, and you're going to, by the way, always pick these up by the glass. These droppers, people love to play games and leave them halfway undone, so you get them about here and they go all over you and all over the table. And then the other thing is that the stains themselves, most of them are dissolved in some sort of alcohol and they eat the rubber. So they will fall apart. We have to change the tops about once a year because they all dissolve rubber. So anyway, you have your knife in your gloves, in your outfit. And by the way, where do you do your stain? Most people think we do it on these screen sinks. We do not. We don't because people splatter and because the material that was on those sinks will stick to your slide. So you press this 3 times and you make yourself a little staining area. You lay your slide there and then you take a drop of methylene blue and you put enough to cover the circle. And you let it set there about 60 seconds. Now, 55 seconds is fine, 65 seconds is fine, 120 seconds is fine. It's not that exact, but not 10. So, you're going to leave it on about 60 seconds, and then when you're done, you're going to pick up the slide and you're going to shake it off into the sink. Shake it off. And then you're going to take the water bottle that we have, and if this is your slide, and here's your little circle, you're going to aim the water here and here and let it run down. You are not going to aim it at the circle. That will overwash it. And we do have a terrible problem with about 90% of you. 90% of you are freaks. It's got to be clean! Clean, I say! Every bit of it. Gone, gone, gone. It's not good for staining. You can wash it all off. So what we want you to do is aim it above and let it run down until the water is pastel. Still barely blue. Stop. Shake the rest of the water off. Take a piece of paper towel, fold it over, and blot it dry. Don't scrub, just blot. Then put the oil on it and focus it. And you focus it by putting it in the slide holder, bringing the condenser up. You've already got the oil on it. And click the 10x into place. Bring the stage all the way up. And then all you have to do is go down just a little bit and fine tune. Swing the oil objective into place, fine tune. There you go. So the simple stain tells you size and shape. Now in virology, we also use the methylene blue simple stain. And we use it because viruses need host cells, and we grow a lot of bacterial viruses. And we want to know if the virus is killing the host cell, because when it kills it, it's released, and we get high virus production. So we often stain a liquid containing our cells with methylene blue, because living cells in their first 5 minutes after receiving methylene blue are baby blue. However, they're killed by methylene blue. So in 15 minutes, they're all dark blue, navy blue, or black. So another sort of FYI is that methylene blue will kill living cells. Living ones will be light blue, dead ones will be dark blue or black. Now, guess what? You didn't think any of this applied to real life? It does. When we didn't have all the fancy antiseptics and antibiotic ointments and Bactrin and all those triple antibiotic ointments for when you cut your finger, you know what we did? We sprayed it with crystal violet or methylene blue. Even for the cards, What cards should you make for the next time? Gram, Induscore, acid fast, but we won't be going over them because we'll be having a test and we'll be going further on into the chapter on the microscope. So you really basically have a week to do those things. And they're already done and other things. Oh, one of the things I told the other class that I didn't tell you, and that's because I like them better, was that if you are one, if you're very thorough, two, if you're like me, always looking for a shortcut, even though it hurts you, you will have perused the website like I told you to and looked under every button, and you will have found the cards are already there and already done. But it won't do you any damn bit of good. It is for this. Do your own. Put your own there. Put it in your own words. That's what you'll remember. But then you can go to mine and see if you left anything out. But don't start with just mine and make yours from it, because you won't learn anything and it won't stick. Do it the right way. But you can do it any way you want, and we'll pay the price. All right, so let's go with what we were doing tonight, and that's the lecture on introductory notes.
I have a question.
Yeah.
So what cards are we supposed to have done already?
Right now, you should have done how to properly wash a slide, preparation of a smear from auger, preparation of a smear from broth, the simple stain and the negative stain. And by a week from today, you should have the gram stain and the score stain and acid.
And all this gonna be on the test?
The only thing what's going to be on the test is from boing, this point backwards.
Okay.
Everything from now backwards except for the discussion about the gram stain.
Mm-hmm.
Okay?
Now, do you want the cards as an actual card already? Are we turning
Not
these
yet.
in? Or?
When we get to next Thursday, I would like for you to have them either on a sheet of paper typed out so you can follow the instructions,